Let us start today's class. Today, at the very beginning, we'll be discussing on a current carrying loop that is placed in a uniform magnetic field. When a current carrying conductor is placed in a magnetic field, this effect is called motor action because here we are getting mechanical output from electrical input. Suppose we have a magnet, this is the north side. A conductor is placed in this fashion and this is the south of the magnet. Fields are moving from north to south like this way, and the direction is in this direction. We have infinite numbers of field lines from north to south. Suppose we are applying some voltage here for which a current is flowing through this wire. So if this is the current flowing direction, so current will be flowing in this direction and it will come back to the negative side. If current flows through a conducting wire which is placed under a magnetic field, then this wire will experience a force. Before we find out the magnitude and the direction of the force exerted on this wire, let us draw the side view of this figure, that means looking from this side to have better understanding. So if we draw, then this will be the north side and the conducting wire will be looking like this. This is the south side. Fields line are moving from north to south with a magnitude B. In this conductor, the current is flowing into the page. That means if you look from this side, the current is flowing into the page for this conductor and the current is coming out of the page for this conductor. Let us denote different sections of the wire by different notations like A, B, C, D. So we have A, B point here and C, D point here. As we can see, two opposite direction currents are flowing in these two wires. So it is evident that the force experienced by these two wires will have the opposite direction. We'll figure out the directions by drawing the vectors, but as they are experiencing oppositely directed force, so you will have a rotational effect, and that rotational effect will have a center point here. From these center points, the distance of each wire can be taken as r. Hence, instead of showing the linear force that is exerted on this wire, it will be wise to express the force in terms of the rotational equivalent of the linear force, that is torque. The linear force of each segment of the loop can be expressed by this equation F equal to I into L cross B, where I is the current magnitude that is flowing through this wire. You can write I here, and L is the length of this conducting wire. So we can express this length as L, and B is the magnitude of this magnetic field, which can be written here, which is also written here. Here you need to understand that this L, length L, will have a magnitude and direction, and this direction will be defined to be in the direction of current flow. So if the current is flowing from A to B, so this length is the magnitude and the direction will be from A to B. In this way, by seeing the direction of current flowing, we can figure out the direction of the length L. Hence, the torque on each segment can be represented by tau, which is equal to force applied, that means linear force applied, that will be multiplied with R, I mean from center to distance of the conducting wire that is rotating sine theta. Theta is the angle between the vector r and vector f. Now we'll figure out the force and torque for each segment of the wire so that it becomes very clear to you how it's operating. First, we'll start with segment AB. In this section, the direction of the current is into the page. So it's into the page. If we see this section, AB section, which is drawn with this side view here, we can see the current is flowing into the page as it is moving from A to B. So the current is flowing into the page, while the magnetic field B points to the right. So this is the magnetic field B direction. As direction of current represents the direction of length L, so L cross B, that means L is towards the paper and B is pointing towards right. So L cross B, that will give us the direction of force, which will be downward. So this will be the direction of force. So we can write F equal to I into L cross B, which can be written as I L B, and this is pointing downward. I'm just writing down. So this is the direction down, and this is the magnitude of F. Hence the resulting torque tau AB for AB section will be F into R sine theta. Theta can be written as theta AB, angle difference between this R vector and F vector. We can see this is the direction of R, as this is the direction of R for this AB section from center to the conducting wire. So this is the direction. If we draw a parallel line with this, so this will be the direction of R, and the angle difference between this R and F will be theta AB. So this is theta AB, this angle. As force exerted on this wire is downward, angular force that is represented by tau AB will have a clockwise direction, that means in this direction. So I can write tau AB equal to F R sine theta of AB, and the direction will be clockwise, where F can be represented by this ILB value. So ILB sine theta of AB. I think this question is clear to all of you. Let's go for another sections. Segment BC. For this segment, the direction of B is towards right as usual, and the direction of the current that is moving from B to C, which gives the direction of length L. So as it is moving from B to C, so the direction of L will have this angle. So we can write a line parallel to this here. This is L. Now the L cross B, which gives the direction of the force, will be into the page. So the force will be into the page. We can write F here, and that is into the page. So F equal to I L cross B, where L and B both are vector. So we can write in magnitude I L B, and that is into the page, as we have written here. Now for this BC section, we can see is R and L, they are in parallel. As they are in parallel, angle difference between this R and L is 0. So we can say theta BC is equal to 0. Hence we can write tau BC, that means torque exerted due to this BC section, will be F into R of sine theta BC, which will give you as theta BC equal to 0. Sine 0 will return 0 value here. So the tau BC will be 0 here. Similarly, for other sections, like for segment CD, the segment CD will have the opposite conditions of segment AB, where the current is coming out, field is having towards right direction, that will be, if you apply Fleming's left hand rule, you will get the direction of F, and that is upward. This is the direction of F. Similarly, the direction of R will have this direction, and this angle difference between R and F can be denoted as theta CD. In this case, we can write tau CD equal to F of R sine theta CD, which can be written as R I L sine theta CD. Similarly, for segment DA, which is equivalent case of segment BC, we can get torque tau dA equal to 0. Here I forgot to write, the direction of tau CD will be clockwise. As the force is exerted in this direction, we can see it from here. The force direction is upward, so force direction is upward. So this wire will have the rotational force in clockwise direction. So this will have a clockwise direction CW. Now what will be the total induced torque? Total induced torque is the torque at segment AB plus torque at segment BC plus torque at segment CD plus torque at segment DA. Let us segmentize this portion. Now the tau induced will be equal to tau AB plus tau BC plus tau CD plus tau DA, and we can see that tau DA and tau BC, they are having 0 value, so tau induced will be tau AB plus tau CD. Here tau AB equal to ILB. Oh, I forgot to write R here, because F equal to BIL, as we have got from here. Let me put R here. So it's RILB sine theta AB. Here it is RIL. Oh, here I forgot to put B. So here it is RILB sine theta CD. So which can be written as RILB sine theta AB plus RIL sine theta CD. Now this is what we have got our tau induced. Here theta AB is this angle and theta CD is this angle. We can see for any position of the wires, that means conducting loop, this theta AB and theta CD, they are equal. So we can write theta AB is equal to theta CD, which can be considered as theta. So tau induced can be written as RIL magnetic flux density sine theta plus RIL B sine theta, as theta AB equal to theta CD equal to theta. So we have replaced this theta AB and theta CD by theta. So we can say induced torque or total induced torque can be written as twice R I L B sine theta. Now this is the equation for total induced torque. I want all of you to understand this equation. Suppose you want your motor to have higher amount of torque. What do you mean by higher amount of torque? If the motor has higher amount of torque, it will be able to move with higher amount of load. That means it will have more angular force, so it can move with higher amount of load. So if you want to increase the motor torque, so what you need to do, either you can increase the current flowing through the wire, conducting wire, or you may increase the magnetic flux density by using a very high valued magnet. Once the motor is constructed, you cannot change the value of L and R. So what you can change, the value of I can be changed by changing the supply, and the B can be changed by changing the supply of the excitation of the magnetic field. If we have current carrying conducting loop, suppose this is a current carrying conducting loop, and we have a formation like this. Here the source is applied, plus minus, so current is flowing in this direction, in this direction, in this direction, and it's coming back to negative side. So what will happen, this current carrying conducting loop will produce a magnetic field. What will be the direction of that magnetic field? The direction of the magnetic field will be upward. How can we get that? If we take the cross section of this side, cross section of this portion, so we are taking this cross sectional plane. So how the thing will look like, we'll see. We have a circular magnetic field due to this wire and this wire. So if we draw the side view, it will look like this. So you have this wire and this wire. This wire represents the right side wire, and this wire represents the left side wire. Here the current is going in, that means into the paper, and here the current is coming out. So you can write in this fashion. So two magnetic fields will be created due to this wire. So one will have this direction and another will have this direction. Now we'll have infinite numbers of magnetic field around this wire, so we can write more, and the directions can be written like this. And we know the basics from our previous lectures. So if we add all the vectors here, we'll get a summation of magnetic field which will be directed to this direction. So we'll be getting magnetic field due to this wire that will have this direction, due to this wire that will have this direction, and due to this wire that will have this type of direction, and due to this side another magnetic field will be there. All these magnetic fields will be summed up and give a total magnetic field which will be directed upward. I hope you remember the construction of solenoids. If we have an iron core like this, if a coil is placed and the coil is given positive supply here and negative supply here, so current will be flowing in this direction. So if we take the case for each loop, we'll see that there will be creation of magnetic field due to this wire and this wire, and all the magnetic fields will be summed up, and there will be a resultant magnetic field which will be directed towards this direction, and another magnetic field we can get that will be directed towards this direction. If we draw all the magnetic field, that means summation of all the magnetic field vectors due to each portion of the wire, we'll get a magnetic field that will be moving from north to south. This will be the direction, and this will be the case for other side as well. In this way, we can plot all the magnetic fields even in the 3D view. One thing we need to understand, if we increase the flow of current, then the magnetic field will be increased. That means magnetic flux density will be increased. If we decrease the current flowing, then the value of B will be decreased as well. If there is no current, that means zero current, ideally the value of B will be equal to 0. Now what will happen if we provide an AC supply instead of DC supply here? So if we provide an AC supply here, that means AC supply, so what will happen? The nature of AC current will look like this. If we plot the AC current, this is the positive maximum, this is the negative maximum, then the wave shape will look like this. This is the sinusoidal wave. This x-axis represents time t, and this is the magnitude of current I. Suppose current I is flowing through this wire. This is the positive maximum, and this is the negative maximum. Now if we plot the vector v here, so b will have 0 value when the current is equal to 0. Now as the current increases, suppose it comes here, so the b value will also be increased and the direction will be in this direction because it's going positive. So it's, if you consider the positive direction is having this conventional direction, then b will be having from right to left. So right to left we are considering this vector. As I increases, so the magnitude of b will be increased. As I increases more, then b will be increased more, and after some times b will reach to its maximum value. So this is the maximum value of b. This is b max. Now again the current will start decreasing, so the value of b will be decreased. Then current comes back to 0 position, so b will also have 0 value. Then current starts increasing in the negative side, that means current changes its direction, so it will be flowing in the opposite direction. So what will happen? B will be increasing. Suppose we are having this negative value, so B will be increasing in the negative side, that means opposite to the previous side. That means this side, if initially this side was north and this side was south, then when current changes its direction, this side will be south, this side will be north. So we'll be having oppositely directed magnetic field. So as current increases in the negative side, so this value of B will be increased but opposite to the previous case. So it will be increased and it will reach up to a maximum value. When current reaches to its negative maximum value, then again current starts decreasing, so B will be decreasing, and when current comes back to 0 position, then B will also comes back to 0 position. In this way, as we are having alternating current, we will be getting an alternating pulsating magnetic field which will go back and forth in this fashion. Now what will be the frequency of changing B? It will have exactly same frequency as we are having for supply current. So the frequency of B will be equal to the frequency of the supply current, and the magnitude of B depends on the magnitude of the supply current. These concepts will be used while designing AC machines. We are going to conclude our AC machines fundamentals part here. From the next class, we will start our very first AC machine, that is 3-phase induction motor. We'll continue in the next lecture.